Okay, let's get into radicals and radical functions. So we're going to start with square roots. Square roots is kind of the entry level of radicals. And I'm sure a lot of you guys have already seen this before, but the idea is that if I'm squaring a number, let's say I have 5 squared, I get 25. But also another observation is if I take -5 squared and then -5 is parentheses, -5 times -5 gets us positive 25. And so a square root is trying to undo that. Square root of 25 is 5, and if I take the negative outside of the square root, then I would get a -5. I can't have the negative inside the square root unless I'm dealing with complex numbers, which I'm not sure if we've covered up to this point or not. But for now, let's just say that we want to avoid that. So if I have a negative outside, I'll still get a real number, -5, after I take the square root. Oh, well, there we go. Now, if I'm dealing with powers or exponents, square roots seem like they're behaving a little bit differently, and so the process is going to feel different, but it's the exact same concept. We're undoing a square, essentially. So when you're doing the square root of x to the 8th, what you do in order to evaluate that is you take your power and you divide it by 2. So 8 divided by 2 gets me 4. And that's true for any power. So if you had x to the 10th, and you're taking the square root of that, you would get x to the 5th. So here are a few examples real quickly. Square root of 121 is 11. Maybe I would recommend just in general to kind of have at least up to 11 squares memorized. So like 1 squared is 1, 2 squared is 4. 5 squared is 25, that stuff, because that will help you with, math in general, but specifically with factoring and stuff like that as well. Square root of 0 is 0, because 0 times 0 is 0. If I have a fraction and I'm taking the square root of the entire thing, I can break my square root up into 2 different parts and say, okay, I don't really know how to deal with 49 over 4 being square rooted, but I do know the square root of 49. I know the square root of 4. And so I'm going to break up my square root and give me square root of 49 is 7. Square root of 4 is 2. Now, sometimes we can have numbers and exponents. So if that's the case, square root of, we kind of go piece by piece. You take the square root of 81, we get 9. We take the square root of y to the 6th, and then we use what we saw in the last slide of dividing the 6 by 2. So square root of 81 is 9. Square root of y to the 6th is y to the 3rd, and then I just put them together, I get 9y to the 3rd. If I have a negative outside of my square root, I just get the whatever the square root is, and then turn it into a negative. So square root of 36 is 6. Just so happens that I had a negative outside, so my result is still negative. Square root of -36 has no real solution. Again, if we've covered complex numbers, we know that we can kind of find a different answer, but it's definitely no real solution. There's no real number that I can multiply by itself to get a -36 or any negative number. Now, sometimes this is kind of the nice situation that like 121 has a square root. It's 11 because 11 times 11 is 121, but that's not always the case. Sometimes we take the square root of things that don't have a nice thing that can square to it. So if that's the case, we just use our calculator, and we generally have to do squiggly equal signs because we typically have very lengthy decimal answers. I don't want to say that we're always going to have a very lengthy decimal, but I can't really think of a root that isn't nice and has a very nice decimal answer. So all of that being said, you might just have to do squiggly lines and round to 2 digits. Cube roots are very similar. They're kind of like the bigger brother of squares. Instead of taking something to the 2nd power, now we take it to the 3rd power. So 2 times 2 times 2 is 8. And so to undo that cube, we take the cube root of 8 to get 2. And so it looks just like the square root symbol, just now it has a 3 in front of it. And that's true, honestly, for any root. So you can have a 5th root, it looks like a square root with a tiny 5 there. And so some people write square roots with a little root and then a 2 if you want to, that's perfectly fine. But the standard is kind of just a square root, so that's why we usually leave that out. But something's interesting about cube roots and cubes is that we can now have negative numbers. This slide's a little bit wrong. So if we are trying to find -2 cubed, well, -2 times -2 is 4, times -2 gets me -8. And so I can actually undo that and say, okay, well, if I take the cube root of a negative number, there is a negative number multiplied by itself 3 times. That gets me a negative result. And so that can happen. Which again is just what I just said. And now when we're dealing with variables, it's a very similar process. Instead of dividing by 2, we divide the powers by 3 now. So x to the 9th, well, the cube root of x to the 9th is 9 divided by 3 gets me 3. So x to the 3rd. Kind of similar, we're going to see a batch of examples right here. Cube root of -27 is -3. Perfectly fine, we can do that. Cube root with fraction, again, we can just break it up into pieces. So cube root of 27 over 64 seems terrifying. Cube root of 27 is 3. Cube root of 64 is 4. By the way, since I'm thinking about it, we generally don't deal with cubes much higher than 5. So I would recommend memorizing 1 through 5. If you want to go beyond that, all more power to you, but you won't see any questions. Honestly, I would be surprised if we saw something bigger than 64. But so don't feel like you have to memorize up to 10 or whatever, like we did with the squares, or like I suggested with the squares. And then if we have a number and a variable, just like last slide, we take the cube root of the number. So cube root of 125 is 5. And then the cube root of x to the 18th is 18 divided by 3 gets me 6. And then I just put them together. And then I think that last thing's left over from the last slide. And so as I was talking about with a cube root, once we get beyond 3 or 4 or 5 or anything like that, we just always put the number right kind of above that little square root symbol. And so some pattern that you might notice if you start kind of throwing things in your calculator or evaluating things is that when that n is odd, so a cube root, a 5th root, a 7th root, on and on and on, and we have a negative under that thing, it's fine. We'll get a real number. It might not be nice, it might be a decimal, but we will get a real answer. Where if n is even, any even, so square root, 4th root, 8th root, 12th root, any of those cases, and we are taking that root of a negative number on the inside, then we get no real solution. So to see that 4th root of 16 might take you some time, and maybe it might be a bit of a trial and error to just go, okay, what number? Let's see, it's 1 times 1 times 1 times 1. I have to figure out a number that multiplies by itself 4 times. It just so happens to be 2. This is also certainly something you could just throw in your calculator for that guy. Cube root of -243 is -3. Perfectly fine to have a negative under that root. If I have the 4th root of a negative number, though, I can automatically say that I have no real solution. And then if I take the 4th root of 16 times x to the 12th, the 4th root of 16 is 2. I see that on the top of the slide. And then the 4th root of x to the 12th is 12 divided by 4 gets me 3. Now moving into kind of a weird situation or a unique situation, that if I have an nth root and I'm taking something inside to the nth power, then in that case, I don't really worry about no real solutions or real solutions. I'm going to get those. But if I have an odd number, I guess the slide says even first. If n is an even number, so what that would look like is the 4th root of 4 to the, I shouldn't use the same number, the 4th root of 3 to the 4th. Then what I do is the result is going to just be an absolute value of the thing. And the reason for that is, well, once you take the even power inside, it's going to force your thing to be positive regardless of what happens. And then if n is odd, it's just the thing itself. So this is a very specialized case. I'd honestly be surprised if we were tested on it, but it's worth bringing up because if you see it, that's kind of what it breaks down to. So quick example, square root, and I have -3 squared. So those are both n equals 2. So I change it to the absolute value of -3, which just leaves me with a regular 3. And then the cube root of -3 cubed, looking at kind of the formula above, doesn't change anything. Whatever is inside that thing or whatever is being cubed gets me -3. And now this last guy is a bit of a trick question. It seems like I have a square root of a kind of gross trinomial. I don't really know what I'm doing, but I can actually factor that. X squared plus 10x plus 25 gets you x plus 5 times x plus 5, which is equal to the square root of x plus 5 squared. And then using the definitions from above, I can say that that gets me a result of the absolute value of that x plus 5. I believe this is the last thing, evaluating functions. This is something that we've actually seen before when we were just dealing with general functions. Now we're dealing with square roots and cube roots, but that's fine. Same concept applies. I'm trying to evaluate a square root. I'm going to be given a function, or in this case, 2 functions, and then I'm going to be given an input. So for A, I was given an input of 5, and I see that I'm going to use the f function. So I take the f function, which is the square root of x minus 5. I plug in 5 for x, and 5 minus 5 is 0, so square root of 0 is 0, so I know f of 5 is equal to 0. Same concept for f of 8. F of 8 is equal to the square root of 8 minus 5, which is equal to the square root of 3. And then now if I move on to g of 1, I'm going to follow a very similar process, but I'm going to be calling a different function. I'm calling g. So my g is the cube root of x minus 2. I plug in 1 for x, subtract 2 from 1, I get -1, or the cube root of -1, and then the cube root of -1 is just -1. Finally, if I plug in 7, D is not quite correct. It should start with g of 7, not g of 1. But if I plug in 7 into my function of g, then I would get 7 minus 2 cube rooted, which gets me the cube root of 5. And honestly, I would just stop there. So kind of like what we saw in B, if you really want to give me the decimal answer, you can, but then you're not going to be entirely accurate. There's going to be some sort of rounding error. So I prefer that once you get to that final step and you've simplified as far as you can, just to leave it and say, this isn't a nice root, that's not a nice whole number, I'm just going to stop here. Never mind, this is the last slide. Okay, so when we're graphing a cubic, this is just a quick example. And this graphing style, if I haven't mentioned it before, is actually pretty common in math because it's almost universally will get you some information. It might not be a great amount of information, but it might not give you your full graph. It also is kind of can be a bit cumbersome, but it works. And so what we do is we put in, we pick numbers for our inputs. So in this case, our x is our inputs. We're throwing in numbers. I'm going to put in, I just picked, I mean, randomly is a little bit misleading because I know these are good numbers to deal with, but we'll pretend that when you're approaching these problems, you just kind of pick random x's, and so that's what's happening here. I picked x is equal to -8, -1, 0, 1, 8. As a general recommendation, you should do at least 3 points, and one of them should be positive, one of them should be negative, and one of them should be 0. And then once I've just picked these numbers, and again, I chose them, these aren't magical numbers that always work, I'm going to plug it into my function. And so the cube root of -8 is -2, plus 3 gets me 1. Cube root of -1 is -1, plus 3 gets me 2. Cube root of 0 is 0, plus 3 gets me 3. Cube root of 1 is 1, plus 3 gets me 4. Cube root of 8 is 2, plus 3 gets me 5. And all of these are points on my graph. And so at this point, I would sketch a graph on my piece of paper. I would plot all of these points. So -8, 1 is one of my points, -1, 2, and 0, 3, so on and so forth. And so once I plot those points, I kind of have this red graph. And now from here, this is where like I should try and connect the dots. And that's generally how you would approach this. But if you just straight connect the dots, you're going to miss a little bit of the story. And so what a cube root graph looks like is it kind of has a bit of a swoosh to it. So that's a cube root graph, and generally that's kind of what a fifth root graph looks like, and a seventh root graph is you kind of have a swooping from the bottom left or the top left and swoops the other way. And if you're doing a square root graph, it looks exactly like this, except for it's only going to be the right side of our graph because we can't have negatives.